Okay. So, in this lecture, we will discuss the basic difference between March sort and weak sort. Uh, what are the difference in shapes and difference in complexity between these two algorithms? So basically, March sort divides the list from the middle of the list and try to divide it almost in two equal sublist, and they repeat this process. But what we should do, we should divide the list by comparing a keyboard element. That keyboard element can be selected from randomly from the list, or from the first position, or from the last position, or maybe using some different technique. Because we'll discuss later that this selection of pivot element is vital for performance of the picture. So division in merge sort depends only on the length of the list, but division in quick sort is only depends on the selection of pivot element. So this pivot element selection is vital for quick sort, and this actually makes the main difference between these two algorithms. So you've seen in the previous lecture that for milestone there is clear two different steps. One is a set of steps for or different set of steps for division of the list, then for merging the list. Same number of different steps for merging the list. But in the quick sort, we get the final sorted list after only the division steps. So that is why, in that sense, quicksort is weaker than mopsort. So the name came from that phenomenon that there is no margin steps that needed in mopsort. There is only in quicksort. So the conquer mopsort also conquer the elements like margin to sorted sublist, which basically follow the insertion technique, which I have discussed. And quicksort do not need separate merge technique. It is already sorted by the division. After the division of quicksort into the single element, it is already sorted. So there is no need of uh, different steps of combining of the elements. So this makes the quicksort quicker in the sense uh, than the merge sort. So we'll now see we'll now see how actually, in a sense of computational complexity, with Morse and Quicksort is they are same or different. So we can see that best case, worst case, and average case complexity of Morse is allowed, but the best case, average case, uh, the complexity of Quicksort is n log n, but the worst case complexity of Quicksort is n square. And how this is happening, you can analyze it in later algorithmic step, and using the recursion that we used to implement these two technique. Because from that previous example, we can try to understand how this n log n is coming, where this log n is coming. So from this picture of Mars sort, we can see that initially the length of the list was, but it is 8. And uh, how many steps in the division process? There is first step 1, second step, third step. So for length of 8 element list, they are needed 3 division steps. Now, if you see this sublist of 4 lengths, this is 4 length sublist. Then for this four length sublist, how much division step there? How many? One and two. So for the four length of list is four. Then their division step is two. And similarly, if we take here a list of 16 length and then split into two 8 lengths, then the same procedure. Then there will be four different steps to reach the final split of elements. So if the length of it is 16, then there will be four step of divisions. Similarly, if you take 32 elements, it will be. So we can see from this number, there is the pattern like what we see mathematically in action. Uh, that what is situation for first one or trivial case or single one, then second one, then we analyze into a number of problems, a number of elements. So here from we see that for four length of list there is a step division step of two, for eight it is three, for 16 it is four, for 32 it is five, and we can see there is a relation that this 2 divided by 2 is 4. Then again, here 2 by 3 is 8. That is 2 power of division steps equal to the length of list. Then here 2 to the power 4 equal to 16. Then here 2 to the power 5 equal to 32. So similarly, if we take n element of list, then there will be the power x, 2 to the power x steps, division step, and from these we can calculate that x equal to, from the log formula, log base 2 n. So from here we deduce that for n for a list of n number of elements for length n, there will be division step in merge sort, that is x equal to log base n. So there is log 2 base log n division step, and another log n conquer step, combining step, merging step, and the log n same number of steps. And in the combining, we are using that we are inserting the elements into a sorted sublist every time we are using that. And if we take the last margin, that n by 2 element of sorted sublist of two n by 2 elements sublist are merged into n element, and this there needed error is n comparison. So for comparison, there is almost n steps. So total complexity will be log n plus log n into n. So this become 2n log n, or we can say order of n log n. So from this basic steps and from this basic example, we can deduce that the original complexity of merge sort is order of log n. Then the maximum upper limit is n log n. The order of n log n. The maximum upper limit is n log n. So similarly, if we sort, we see that there is that conquering step is single, but the division step is also number of division step is n log n, and combination or concurrent step is single one n. So it is also of on n log n. It will be of order of n log n. So from these we can say that this best case and worst case and average case complexity of also is n log n, and the best case and average case complexity of quicksort is n log n. But the worst case complexity of quicksort is order of n square. Now we will see that what is the worst case scenario of quicksort. So now we'll see the what is the quicksort worst case scenario of quicksort. Worst case scenario of quicksorts depends on the selection of pivot element. We have earlier uh, said that this selection of pivot element is inclusive. See, in this example, the pivot element was selected, the last one, and it is 3. For example, say, say, if the pivot element is selected the first element, that is the 9, then in the first division process, what it will happen? 9 will be the pivot element, the middle element. Then in the sublist, sublist, all the elements that equal less than 9 will come into the left sublist. Then there will come -3 will come here, 5 will come here, 2 will come here, 6 will come here, 8 will come here, more, 6 will come here, and 1 will come here, 3 will come here. So in the right sublist, that is in the division, the right sublist, it's like there's no element. So if we select the pivot element as 9, then the list will be sort divided into like this. Into the only element in the middle, right sublist will be blank. There is no right sublist, and all other elements are less than as it is all other elements. So less than line 9, it will come to the left sublist. Then in the next step, we have divide this left sublist, divide left sublist. Then again, if in the left sublist, if we take maximum that is 8 as pivot element, then again it will divide like this. The middle element, the pivot element is 8, and all other elements that might be 5, 6, 6, 1, and 3, all elements left sublist. So in the every division, there is splitting only one element, and all other elements are coming into the left substrate. So in this way, if you take list of 8 elements, in first step division, it will be n minus 1 elements and 1 elements. Two elements. Then n minus 1 will be minus n minus 2 elements and 1 elements. Then it will split into n minus 3 elements and of 1 elements. Like this, there will be a step of n step. So we see that we have seen that the division step, or if the list is divided properly, approximately in the middle, then the division step number of division step was log of base 12. But if we always select the pivot element at the maximum element, this is the worst case scenario of quicksort. then there will be different number of division steps of n. And in that case, the a log n, this log n, sorry, and this n log n, this log n replaced by n, so it is a into n, that is equal to order of distribution. So in the worst case scenario, the complexity of the quicksort will become order of n squared. And the worst case scenario happens if we select always the maximum element or the minimum element. If we select the minimum element of the pivot, that this situation also can happen. And then in that case, if we select the minimum element as pivot, then left sublist will be remain blank. Middle one will be the pivot element, and the right sublist will be the rest of the n minus one element. So this is the complexity analysis we can derive in this simple example. So that is why the worst case scenario complexity is quicksort is order of n square. So now then we can just list the point-wise difference between mass sort and quicksort, and some of each we can discuss in detail in the next lesson. So in partition of elements in the array method versus quicksort, the quicksort split the array in elements in any ratio, not necessarily divided into same number of length. But in mass sort, the array is sorted into parts, approximately two equal lengths. And for the worst case complexity, which sort complexity is the order of n square, not sort is the order of n log n, which sort works well on smaller arrays. Uh, so it is faster in small arrays because if worst case scenario happen in small arrays, then also it will be of order of n square. And in mass sort, it will effective of that size of edges. And for speed of execution, the runtime, we sort is faster always for small data set, and muscle is consistent for larger size of data. In quicksort, we have seen that there is no needed additional storage because there is no need of margin. But in merge sort, to merge the sorted elements, mark the divided elements into sorted list, you will need another additional storage. In efficiency quicksort, it's inefficient for larger array because of worst case scenario. Mark sort is more efficient in all types of data set, all length of data set. So the sorting method, which sort is called internal and mark sort is called external because of that external storage needed for mark sort. Which sort is called less stable and mark sort is called stable. Big sort paper we perform in arrays, and mass sort paper to be performed in this because in quick sort there is needed the random access that is easy in arrays, and locality of reference, that is the use of cache reference that we will discuss that the next lecture, that in locality of reference quick sort will go and mass sort is go. So this is the end of this lecture where we have discussed the divide and conquer sorting approach, two different divide and conquer sorting approach, mass sort and quick sort, and what are the difference of it, and what are the difference in complexity analysis. So in the next step, we can discuss other uh, sorting algorithms like in sort, right sort, and counting sort. So thank you. This is the end of this lecture.